Hey guys, so going over that problem that we had for homework the other day, we did in class, I just wanted to give a video so that if you needed it, you can pause, stop, take your notes on your own time. But we had this rocket power cart going down an incline, and then going off over a flat area, up another incline, and over another flat area, and you see that setup. There's mu, so there's some friction going into this. And then we have initial velocities, final velocities, and we're interested in the displacement on the second flat that the car goes by the time it stops. Okay. We could treat this with kinematics and forces separately, but if we did that, it would be what we would call the scenic route, and we got into that discussion with block A, but it just takes longer, right? And if we have an easier way to do something, especially if we're going to be in a time situation, like a check-in or the final exam, it's probably better to do it with the shorter way so that you have more time to check over your work and you also have time to get on to the other problems. So remember, these equations that we have here, these equations, they're coming from forces and kinematics. So we're putting them together and creating these new equations. So if we're interested in this displacement here, we can treat this with our equation that the energy that the system possesses before, at the beginning, so right before this cart's about to go down the ramp, plus or minus any external forces that are not the system itself. And when we talk about the energy of the system, whether it's before or after, we're talking about the kinetic energy and the potential energy, right? So E naught refers to the kinetic and potential energy before, EF refers to the kinetic and potential after. Okay, so those are for that object. And then if there's any forces that are happening outside, like friction or thrusts or anything that is not, like when I'm thinking of the system, I'm thinking of just, right, this cart is the system, and then we have some friction going on between, right, we have the surfaces that are going into those forces. So those would be, and plus or minus, because it's going to have to be whether you're adding energy into the system or taking it away, and that has to do, how do we know if it's going to be a plus or minus? We would look at this equation, right, the force parallel times the displacement. If the force and the displacement are in the same direction, then you're talking about an addition of work, right, a positive gain of energy, gain of kinetic energy, and then if you are dealing with opposite signs, so the force is in the opposite direction of displacement, then that would be a negative work, right? You're taking some energy out of that system. So this highlighted equation is where we're going to start, okay? So we have E naught plus or minus work external is equal to EF. Okay, pretty simple. And then what we're going to do is we're going to expand this equation out, because right now, like, I don't have any numbers for this. I'd have to calculate it, and I'm going to expand this equation so that we can figure out what we need to put in for calculation. So remember, E naught, we said, is the kinetic energy initial, and the kinetic energy, or the potential energy initial. So we have that over there. So you know what I'm going to do? Let's just keep some color coding here so that you can see where these are coming from. And then I'm going to scroll back up to our diagram to figure out the work external. So again, anything that has to do with forces, or parallel forces to displacements, is going to be work external, right? Because we're taking care of the height difference, the MGH, the gravity work is being done in the potential energy, the kinetic energy with the velocity is 1/2 mv squared. So anything outside of that realm is going to be our work external. So we have 3 different places where that's happening. Okay, so we have, right, the idea that there is some friction. There's actually 2 places that there's friction. So that is 2 places where there is going to be work that is external to the system. And then we also have the rocket thrust, that is another external force over displacement. So the frictions, right, the force of friction, if we were to just draw a free body diagram real quick of the cart on the ramp, right, remember we tilt our axis, so we have mg, we have the normal force, we are going to have the thrust, and the force of friction, and our displacement is going down the ramp. Okay, so the force of friction is in the opposite direction of displacement, so we are going to get a negative work due to the force of friction, and we're going to call it 1 because that's mu1. Okay, and then in this same displacement, we can see that the thrust is going down the ramp just like displacement is going down the ramp, so that's going to be an addition of work from the rocket thrust. Okay, and then over here with the mu2, right, again, free body diagram for this object, we're going to see mg down. I'm not tilting the axis because we are not on an incline, and there's no rocket. The rocket turned off here. That's what engine off means. At this spot, the rocket is no longer going. But the cart still has motion, right? We just lost the acceleration due to the rocket. And then we have some friction here, so we have a force of friction going back. And our displacement, again, is going in the opposite direction of friction, and that happens every time, right? Friction, by definition, is always in the opposite direction of the motion, or intended motion if we're talking about static friction, but here we have kinetic friction. So we're going to, again, subtract the work due from the force of friction in that second part. So these are two different forces of friction. They probably don't have the same delta x. It is possible for this delta x to be calculated 16, but it's not the same as the 16 meters over there. Okay, so that is where we're getting the plus or minus work external from, by looking at our diagram and figuring out where there's other forces that are parallel to displacements at in different portions of that. And then we are going to get an EF. And again, when we're talking about the energy, we're talking about the kinetic energy plus the potential energy, and in this case we're talking about the finals. Okay, so this is our big equation right here. This is the physics of things. Somewhere in here is going to be how we are going to solve for our answer, because this displacement that we're looking for has to do with the force of friction, right? So even though we've expanded out this equation, the first equation that we had, we're still looking at variables that are defined by more equations, right? Kinetic energy is 1/2 mv squared. So what I'm going to do is, I mentioned a second way, because we kept expanding this in a vertical fashion. I'm going to set up a table just so that it might be a little bit cleaner for people to see the work out. But as we're looking at this, right, we have these different works or energy values that we can define and get answers for, and then we can plug back into this equation up here. So our first thing, my first column, so this is just another way to organize our work. Okay, all I'm doing is showing a different way of organizing our work, right? So we have the energy associated with the kinetic energy of the object, and then we would have the potential energy to begin with. And then in these other sides of the boxes, we're going to be defining the equation, and then we're going to be plugging in variables for the equation, and then we're going to go from there. We have the work from the force of friction 1. We have the work from the thrust. We have the work from the force of friction 2. And then we have our final kinetic and potential, KEF and KE naught, or and UGF. Okay, So from here, what we're going to do is just start defining like what equations will we need to solve in order to get the values of these variables, right? So Ke naught, remember kinetic energy is 1/2 mv squared, and this is specifically going to be the initial velocity squared because it's the initial kinetic energy, right? So this is, if we want to name these columns, this is the energy / work, like what are we defining it? Here's the equation for it. And then we're going to solve those equations, okay? And I'm just going to define these equations. So UG, right, remember UG is potential energy is mgh. And we're going to say h naught. And remember, it's the height, when we're talking about the initial position, it's the height compared to some height 0, and you get to define where the height 0 is. Now, with these external works, you are going with the basic definition of the force parallel times displacement. When we're dealing with potential energy, it's the same thing. It's mg is the force of gravity, height is the displacement that it's going to drop. So we're still always using the same equations. We're just going to be defining it by, again, this force parallel times the displacement. So if we're thinking about the work of the force of friction for the first one, we're talking about when it's going down the ramp here, right? And the way that we're going to define that, the force that is parallel is the force of friction, and the displacement is going to be, right, force of friction 1 times the displacement, which I know is going to be 16, but I'm just defining by variables here. The work of the thrust is going to be the force of thrust times its displacement. What work of force of friction is going to be the force of friction 2 times its displacement. Kinetic energy final 1/2 mvf squared, and the final potential energy is mghf, where the height that it lands at. Okay, so here we're just expanding. We're saying, how are we going to define these variables? Now we can expand the work for our friction one step further, because the force of friction is calculated itself through another equation. So that's where physics gets a little difficult, because we're within equations, we have more equations, right? And that's why when we're looking at this problem in class, it gets real complicated real fast. So we define the force of friction by the normal force times mu, right? This is the force of friction times the displacement. And same thing for this force of friction would be the normal force for this second times the mu for the second friction times its displacement. Okay. So now we can start plugging in, and I'm going to put an arrow to separate, to show you like, okay, now we're going to be plugging information in. So if I look back up, the initial velocity is 0, the mass is 35, so this is going to be 1/2 m, 1/2 35. Right, so velocity is 0. I'm just going to like show it out just so that we can see that we are getting an answer of 0 here. You don't even need to do this. What you can do is you can strike through and say velocity is 0, so my answer is 0, right? And I'm going to do that over here. Our VF is 0, so our final kinetic energy is also 0. Now, if I want to be able to plug in for UG, for the potential energy, I know the mass, I know gravity. Remember, we can use 10. You can use 9.81 if you want. Use 9.8 if you're in the real world. So like here, let's just use 10 to make it easy. In order to plug in a height, we need to define h0. The ground is a place that you can put h0. But let your height 0 help you in some sense. Because if I were to put, instead of on the ground, if I were to put the height 0, oopsies, at a spot where you either start or end, and I'm probably going to put it where I end because it's a little bit below where I start, I'm going to call this h equals 0. because now if I go down to this UG final, the potential energy, HF now becomes 0, right? And now I'm saying that there's no potential energy at the end, okay? Now if I do that, right, since this is 4 meters up, right, if this is now defined as the 0 point, the top where the cart started is no longer 12 meters above my 0 point. It is 12 meters above the ground, but if I'm calling 4 meters above the ground the 0 point, this distance right here now becomes 8 meters, okay? And that's what I'm going to put in H naught. Okay, so you have to define the 0 point. You can make it the ground, that's totally fine. You just need to make sure that you define it. So I'm going to put an 8 here, and then we can get an answer. If I could get a calculator, I get 2,800 joules. Okay. Okay, so now we actually just have to deal with the external forces and their work, because we have 0 kinetic energy because we start with 0 velocity. We have 0 kinetic energy to end because we have 0 velocity. We are ending at what we're calling 0 height, so we have no potential energy there, and we have some initial potential energy. So now we just need to calculate our work due to the external forces. I'm going to start with the middle one because that's the easier of the 3. Force thrust given our problem is 40 newtons, and it happened over 16 meters. So we're going to get an answer of 640 joules. Okay. So now when we're looking at the forces of friction, we now need to be able to, we know the mu's and we know the delta x's, or we're looking for delta x, right? This is the question, okay? So we need to be able to find the normal forces, and this is just going back to our force unit. So I already drew the free body diagrams over here. So I'll start with the one that is not on an incline. We'll start with the last one, and remember, this object is not moving up or down. If we have forces in multiple places and multiple dimensions, then we need to break it into their components. So the F net in the y direction, there is no acceleration in the y direction, so the F net is 0, right? Because ma, the acceleration is 0, then the F net has to also be 0. So we can say F net is equal to normal force minus mg equals 0. So we get this nice equation that says the normal force is equal to mg. And this is true, right, where the normal force is situational. In the situations where the only two forces in the x direction are normal force and mg, and there's no acceleration, the normal force happens to be mg. So I'm going to come and plug that back in down here, and that was for the second part, right? We're going to get normal force is mg, the mu, I'm sorry if I'm scrolling, I'll try to not do that, 0.02 or 0.2. Well, let's keep it at variables and then plug in from there. I'm going to say mu2, and then displacement. So we have one more. Mass 35, gravity 10, mu 0.2, and we do not know this displacement, so we have to keep that as the variable, and every other force we should be able to calculate, so our work and energy that we can calculate, so we can plug into the equation and solve for this x, right? So this is the question. What is this going to be? Now, normal force for our first case here, just going to move this. Okay. Remember, we're on an incline. Okay, so we have mg going straight down. Mg and normal force are not in equal and opposite directions, so they are not equal to each other, but we do have the components of mg, right? mgx, mgy. And what we can say, there's only two y components, and again, we're going to say F net y is equal to ma, a is 0, so F net y is 0. The normal force minus mgy. Normal force is equal to mgy, right? Only the y component. And we defined mgy as mg cosine theta. And right now we don't, if we can find mg cosine theta, then that is the normal force and we can plug that in. What you need to do is to be able to find theta, and even though we don't have it, we can find it because we know what the hypotenuse of the incline is, and we know the y height is 12 meters. So we can do a little bit of trig over here, right? If we have 16 by 12 with a right angle, we can solve for this angle, right? Because we know that this angle refers to the angle that mg makes with the defined y-axis. So we can use the sine function, right? Sine theta is opposite over hypotenuse. And if we do the inverse of sine, right, because we want theta by itself, opposite is 12, hypotenuse is 16. In class I didn't solve for it, I just plugged it in, but I'll solve for it now just so we can get a number for our angle. Inverse of sine, 12 over 16. I get an angle, oh Jesus, I get an angle of 48.59 degrees, and again this is coming from over here. Okay, so we now have found the normal force in this first situation, which is mg cosine 48.59. So we can plug that over here, right? Normal force is mg cosine theta times mu times delta x, and plug in some numbers, right? 35, 10, cosine 48.59, delta x, and this went down that 16 meters. So we can get an answer here. I'll take the cosine of this equals cosine, cosine of that times 10 times 35 times 16. I'm getting 3,704.1 joules. Okay, so now if we look at our work, we have answers for all of these parts except for the force of friction 2, the work done by that, because it contains the variable that we're interested in. So now what we can do is we can take this equation, and I'm just gonna, oopsies, copy. We can bring it down here and we can start plugging in. We can potentially start plugging in. Paste it, cool. Okay, so we're gonna take this, and our kinetic energy initial is 0. Okay, so all I'm doing is writing a line. We have 0 plus 2800 minus, right, the work done by this friction, or by this force. So, right, I know that the force of friction is negative. It's taken care of in the fact that I am subtracting it. So I'm not subtracting a negative. The negative is already taken into account when I said that we are going to subtract the force of friction. So we got 3704.1. We are adding the work of the thrust, 640. We are subtracting, and then order of operations, 35 times 10 times 0.2 times delta x. And both of the other side of our equation is 0. 0 plus 0. Now it just becomes an algebra problem. Okay, we are going to solve. Sorry, I don't have it pre-solved, but we're going to do 2800 minus 3704.1 plus 64. So I'm getting negative, oopsies, negative 264.1. Does that make sense? 28. Yeah. I think my answers are correct. 28 minus 3704.1 plus 640. There, added to that side. And that's going to be 35 times 10 times 0.2, 70, delta x, 264.1 divided by 70. Oh, my answers are off just a little bit. Let me just double check my work. 35. Right, perfect example of things might not always be. Right, 35 times 10 times the cosine 48.59 times 16. Ah, this is exactly what I told you guys was going to happen to you, and it happened to me. What I did not take into account was mu, right? So right here, this is all the normal force. And I totally forgot to multiply this by 0.2, right? So being able to look back in your work and catch your mistakes is huge. And mistakes happen. It's totally fine. But being able to look back and see where that happened. Because my answer, first of all, was having the wrong sign. And also was not what I was getting previously. Okay, that's going to make our lives easier. So we got 20% of that number. My bad. 740.82. Okay, so that minus 740.82 plus 64. Cool. I'm going to get a negative. Okay, nice. Negative 2699.18. Again, because it was positive on the left side, when I move it over to the right side, it becomes negative. And then divided by 70. Now I'm getting 38. Uh-oh. Something else is going on with the numbers here. Let's just double check. Oh, duh, that's 0.3. Miss K. I found mu, but I used the wrong mu. Okay, let's try this one more time. And we should be able to get the right answer. 48.59 times 16 times 0.3. Okay. 1111.22 joules. Okay. One more time. 111.22. Okay. 2800 minus that plus 640. 23. 28.78 divided by 70. There it is, 33.3. Okay, troubleshooting along the way. But the math never lies, as we say. So before I knew I was getting the wrong answer because I should have been getting a positive number on the right side, and it was technically negative at first. And then I knew the answer was 33.3. So make sure, again, double check your work, but that's why it's important to set up your work in a logical fashion as we had here, and double check that your equations and numbers that you have in are correct, okay? So take your time looking over this problem. There's a lot going on, and this is good. I would say, again, this is a level 4 problem, a high level 4, because there's not anything that is particularly new. It's just we're putting a lot of things together.